So it's a 3.2, right? This situation. 2 to the x is 8. What's the answer? X will be equal to 3. But now when you look at the 2 to the x is 10, the only thing we can do is say, all right, well, 2 cubed is 8. 2 to the 4th would be 16, right? And the number 10 is somewhere between 8 and 16. So I know that my exponent has to be somewhere between 3 and 4. And we could estimate it. 10 is a little closer to 8. So my answer probably is going to be a little closer to 3. But we have to be able to solve it. So one of the things that we could do is work on logarithms. And we need the logarithm to be able to solve that one. What about 10 to the x is 100? And then 10 to the x is 30 is what?
Between 1 and 2.
X would be somewhere between 1 and 2. Obviously closer to 1. So, you know, maybe like 1.2, I don't know. But we're going to need a logarithm to be able to solve those. So when you think about it, that's what we're working on. The logarithms, they're the inverse of the exponentials. They'll undo each other. So down in here, we have logarithm form and exponential form. So we worked on the exponential form yesterday. There's a base, some number, gets raised to a power. That will be equal to something. Logarithms. Notice that the base is exactly the same, right? If the exponential is base a, we write logarithm base a. What is this logarithm equal to right here? That logarithm is equal to y. And notice that y is the exponent. So you'll hear me say a lot when you write logarithms. Logarithms are equal to the exponent. That's really by definition what they are. Logarithms are exponents. Some of you have not such hot handwriting. So when you write logarithm, get the base down here on the G. If you write log base something, put the base down here. Whatever you're taking the logarithm of would be right next to it. And then you'd have some answer over here. I don't know, whatever it is. So you write stuff like this. Some of you start writing, you do stuff like this. And now we start to wonder, are you doing the logarithm of 28? Right? So we want to be very distinct. Put the 2 down here, the 8 there, and the 3 is there. So it would be log base 2 of 8 is 3. All right, so these we're supposed to be able to solve with without a calculator, it says. And you simply, at times, when you get to the test, just by switching from logarithm form to exponential or exponential back to logarithm form, the answer will be sitting right there. So for instance, many of you don't know what log base 2 of 32 is. But if I switch to the exponential form, so we go, what's our base in this problem?
2.
Base 2. This logarithm is equal to the exponent. So because this logarithm is equal to y, y is the exponent, and the only thing left then is 32. So how many 2's do you have to multiply to get to 32?
5.
5 of them. 2 times 2 times 2 times 2 times 2. 2 is 2, then times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that works. So if I go to rewrite this one, my logarithm base is 4, so my exponential base will be 4. Logarithms are always equal to the exponent, so y is my exponent. How many times would you have to multiply 4? Or how many 4's do you need to get out to 16? 2. So your y value is 2. And finally, the bottom one here, base is 10. 10 to the y power, because logarithms are always equal to the exponent, so y is my exponent. And I put 1 over 10 here. Yeah, as soon as you see the whole number, 10 is a whole number, and then now it flips into a fraction, you know the answer is negative. the exponent must be a negative exponent to get to flip. How many 10s does it take to get to 10? 1, so that would be your answer right there. Alright, so then this final one is sitting there as log base 3 of 1. So a lot of times we'll put something like log base 3 of 1 on an exam and just say, what is it? And sometimes students don't really get what they're supposed to do. Does anybody know what the answer is?
0.
Okay, well if you didn't, you would make up your own variable. Doesn't matter what variable you pick, just say, oh, I don't know what the answer is. Write it equals W. Now if I go to rewrite it, 3 is the base, logarithms are equal to the exponent, so W is your exponent, and the answer is 1. Well, any base to this power is 1. And you guys said it was 0. Alright, so there's some DIYs. You're going to do these real quick. I'll put the answers up in a second. Alright, so you did these on your own. You're not supposed to use a calculator. Again, you can just rewrite it so it would look like that. This one would look like this because maybe you set it equal to x. And again, maybe set this one equal to x, it would look like this. So when you do that, hopefully you can figure them out. Questions on those? Alright, so then we have what's called a common logarithm, and they're talking about a log function with base of 10. So it's the common logarithm. So when somebody writes logarithm of, say, 20, it's the same thing as somebody else that writes log base 10 of 20. If you're working at base 10, you do not have to put the base 10 down. Or if it's some other base and you forget to write it, then people that read it are going to assume you meant base 10 and you didn't mean it. So log base 10. Our number system is log base 10. Every time you have 10 singles, it goes to a 10, right? And you get 10 tens, it goes to 100. And 10 100s goes to 1,000. So it is such a special number that on the calculator, right next to the number 7, right here, you have its own button. Logarithm base 10 is on the calculator. So all of these are on base 10. It says use a calculator only when necessary. Find each common logarithm. Do I need to do it? Do I need to use my calculator for this one? No, because if it's base 10 and you don't know the answer, you'd say, well, 10 to the x is equal to 10. X would have to be what? 1. Do I need my calculator for this one? Yeah, because 10 to some power would be 1/3. Doesn't make sense. So you can just go to the calculator, hit the log button, 1 divided by 3, hit enter, and it's negative 0.4771. In logarithms and exponentials, 4 decimal places is probably the best because it can really make a big difference in your answer.
Or 7.
What?
Or
7, 7?
Yeah.
1?
Yeah.
Thank you. And then 10, again, log base 10, I need my calculator. So we go log of 2.5. So 3979. 3979. Okay. So quickly do number 2. It's a DIY, so I'll just pause it. You'll work on it. We'll put the answers up in a second. So again, using a calculator only when necessary. Well, you need your calculator on every one of these. So you go to type it in, and those 2 work. And why is this one not working? So remember, we're graphing 10 to the x. And a 10 to the x graph does something like this. It'll never come down and touch -2 unless we do some sort of shift. So we're good? If you don't see a base on the logarithm, you assume the person's in base 10. All right, so then there's some properties here, and excuse me, you already know these technically. So if you don't know them, you can rewrite it in exponential form. Or if it's in exponential form, maybe you rewrite it so you can use your calculator and do a logarithm base 10. I don't know, stuff like that. So we're going to take a look at these properties. Number 3, I refer to as a chunga property. It's probably easier. You'll see what I mean. But because it's log base A and the exponential, so you have a log base A and then an exponential base A, they're inverse of each other. They will undo each other and you'll be left with x. Or exponential base A being raised to a logarithm base A, they will also undo each other. And then the last one is called a one-to-one property. If you can get the left-hand side to be the same as the right-hand side, you can do stuff. All right, the equal sign. So notice that these are both logarithm base 2s. So what can you tell me about the x and the 6? They have to be equal. That's exactly the one-to-one property. So at times we'll do on one side, get it all down to one logarithm on each side, and then you can use one-to-one property. So even if you don't memorize the properties, just by rewriting it, you'll probably see the answer. So again, log base 5 of 5 is equal to x. So 5 is my base. This is my base right here. Logarithms are always equal to the exponent. So x is my exponent, and the other 5 just goes there. Well, 5 to what power is 5? 1. If you look up in property number 2, it's if you're taking the logarithm and the base and the number that you're taking the logarithm of are the same, it's just 1. Now this last one is a little bit different. It's easier if you know the property, but if you don't, you would go, oh, well, it's equal to w. Now it is an exponential sitting there. So if I switch to a logarithm, I would write logarithm. My base in the exponential is 2. So my logarithm base will be 2. Logarithms are always equal to the what? The exponent. What is the exponent in this problem? It's this thing right here. It's a logarithm. So it's kind of a crazy exponent, but it's still my logarithm. Or it's still my exponent. So I write log base 2. So my logarithm is equal to a crazy exponent, log base 2 of 14. Well, my w goes here. So just by rewriting it, what's the answer? W has to be the same as 14, or my answer is 14. What's the property? Number 3, the chunga property. You're taking a base 2 exponential, raising it to a base 2 logarithm, it'll undo itself, and you'll be left with 14. So take a look at some of these properties, see if you can get the answer. Okay? So the first one is the one-to-one. If my log base 10s are the same, x would have to be 2. I would memorize this as the chunga property. Exponential base 3, logarithm base 3, they're going to undo each other. 2 would be left. And simply by rewriting this, 5 to a power gives you a 1. Well, it has to be a 0. Any questions on that one? All right, so now they're asking us to graph a logarithmic function. So we're going to go ahead and graph it. And they're asking us to graph this. My thought process is that it's always easier to graph in the exponential form. So what I'm going to do is rewrite this. That's a logarithm base 2. So I'll go exponential base 2. Logarithms are always equal to the exponent, so y is my exponent. And then I can put my x over here. And I like my tables to be vertical. So which variable will be easier to pick, the x or the y? It's going to be easier to pick the y values this time. So I'm going to do the same numbers that we're used to doing. So let's put the 0 in first. When I put 0 in for y, what's 2 to the 0 power? 1. So now x is 1. And that's going to be over here at 1, 0. Now when I put the negative in, what happens? negative 1 for y would be 1/2. Negative 2 would be 1/4. Negative 3 would be 1/8. So as your x value gets closer to the y-axis, your numbers are going down. So what's happening is here, here, and here. And then what happens when you put the positive numbers in? When y is 1, the output would be 2. When y is 2, the output's 4. And when y is 3, the output's 8. So as you go further to the right, or excuse me, as you go up, I should say, you're going to be at 2, then you're going to be at 4, then you're going to be at 8 or something that's going like this. So logarithmic graphs have what's called a vertical asymptote, vertically on the y-axis right now at x equals 0. So again, on a graphing calculator, I'll just graph one for you. If I just do logarithm of x, what base am I graphing when I type in log of x? 10. So when I graph it, I get a lot of students that tell me the graph looks like this. So they kind of, when you look at the graphing calculator, it looks like that's where it starts. But be exaggerated. Go really close to the y-axis and take it all the way down. Exaggerate that vertical asymptote. Okay? Just like with the exponential functions, does it really matter if I switch the base? No. We did a base 2, now this is a base 3, so it's still going to do the same thing. Get close to the y-axis, go up, hit 1, 0, and then go out to the right. It isn't until I put 2 on one graph that you'd be able to see the bigger the base, the faster it squishes against the y-axis, and the bigger the base, the faster it goes out to the right. So now you can go to a spot in the book, 3.2 example 6, and play around with some of the numbers. Remember this the other day? Natural log is e. So right here they're telling you, if somebody is writing log base e, we can just simplify to ln. Now I don't know why it's not nl for natural log, but it's ln. Probably logarithm natural, I don't know. But again, that's such a special number in math, right next to the number 4, right here. It has its own button on the calculator. So you have a base 10 button and a base E button. So grab your calculator, type these in, just round them off to 4 decimals real quick. All right, so again, you just type it in, go to at least 4 decimal places, and then down here, there's no solution because log base E or ln, it doesn't matter which one you write or think about. The logarithmic graph, right? Does something like that. And so you can't ever plug in an x value that's smaller than 0. We can't plug in anything that touches 0 either. So negative 1 is over here, so it's never coming over here, so that's why there's no solution for that one. All right, so we have some properties for the natural log. They're identical to the log base 10. So let's run through them. If I was going to rewrite this, I might say, oh, well, this could be equal to W. When I see ln, what base am I in? E. Logarithms are always equal to the exponent, so W is my exponent. 1 over E goes there then. What's going to cause E to flip into 1 over E?
-1.
A negative. And then how many e's does it take to get to e? 1. So my answer is -1. That's -1. What about e to the ln of 4? E to the log base e of 4. What property is that? It's just 4. It's the Chunga property. Now if you don't like that, then you have to rewrite it. Since it's a base e logarithm, I'm gonna write base e logarithm. Instead of shortening it into ln, so that you guys see what base I'm in. Logarithms are always equal to the exponent. So in this problem, my exponent is kind of crazy. It's log base e of 4. X or w would go there. So if the log bases are the same, then w or x would have to be 4. This property, sometimes when I do these, I'll just write an e under there to remind myself. E to what power gives you 1? 0. So now you have 3 times 0. Well, 3 times 0 is 0. What about this one? E to what power gives you e? So there must be talking about an exponent of 1. So now you have 4 times 1, which is 4.
I know, but there's no alpha.
So I'll go back to that one. Instead of writing log, if you know that ln of x is the same thing, all I'm doing is trying to exaggerate and let people know that when you're working with ln, it's really log base e. But you still have an ln here and an ln there.
No, I understand that. I don't understand in like how it says e to that. If you.
All of these domains we're supposed to solve algebraically. Then we're supposed to go to the graphing calculator and verify what it looks like. All you have to do is whatever is inside the logarithm, pull it off to the side like we've done with other functions, but now we know.
We say hi, please.
So remember, we're doing the logarithm and they're asking us to find the domain. So you take what's inside the domain, bring it off to the side, and set it greater than 0. Then it's just a simple problem. So anytime somebody's talking about the domain of a logarithm, take the inside of the logarithm, bring it off to the side, greater than 0. So I will subtract 4. Then what happens when you divide by the -1? Flip, and you get 4. So it's saying as long as x is less than 4, or negative infinity up to 4, no square brackets because it can't touch 4. So what they're telling you then is also go to your calculator and just verify. So we're going to type in that ln 4 minus x, and what we see should be a graph that indicates anything up to 4 or smaller. So if I graph it, you can see that the graph comes over. Now it does not stop there, right? So right here, it's not stopping, it's actually going down along that vertical asymptote, but it's getting close to 4, so that should visually tell you, yep, I got it right. All right, so the next one, what about this? Take what's inside the logarithm, set it greater than 0. What kind of graph is x squared? So if I was going to do the U-shaped graph, right? Well, that U is above 0 everywhere, but at 0. So I can plug any number I want in there, and it's going to be greater than 0, except when you try to put 0, what's 0 squared? 0. Is 0 greater than 0? No. So you could say all reals, x not equal to 0, or negative infinity to 0, union 0 to infinity. And then the very last one is very simple again. It's just simply take your x minus 3, greater than 0. Add the 3. As long as your x is greater than 3, you should be good. And if you went and looked at this graph, it would be a logarithmic graph shifted to the right 3. So it's gonna get really close to x equals 3, but you can't touch 3. And that's why it works.